To my channel. Today in this video we are discussing questions from the topic electricity for Edexcel AS level physics examination from the past 4 to 5 years of Edexcel board exam question paper. But this is the fifth video of the series and the link to the first 4 parts are given in the description box. I'll show you how to answer the questions. Here we are starting with the question number 33. The remaining questions, the first 32 questions are included in the first videos. So let us start here. A student set up the circuit shown to investigate the properties of a negative temperature coefficient thermistor. So there is a parallel combination of two resistors, 500, 600, and across that there is a voltmeter to measure the voltage, an ammeter, and there is a thermistor given. So the question is, show that the voltmeter reading was about 6 volt when the ammeter reading or the current flowing is 23 milliamps. As see, the voltmeter is connected parallel to the, or voltmeter is connected to measure the voltage of the parallel combination. So let us say this is a loop. For this loop, this is a loop of this loop 1, or this is the loop across which we are measuring the voltage. So for that, let us calculate what is the resistance of this loop, the total resistance of this loop. So the total resistance RT of loop 1, which is, and we know that we are in parallel combination, we are using the equation R total. It is the sum of the reciprocals of the individual resistors R1 and R2. But in my previous video, I have given a short form, a shortcut to calculate the resistance as the ratio of the product over the sum. And this is a method only when two resistors are used. So I'm going to use this equation here. RT, it is the product of resistors, that is 500 times 600 over 500 plus 600. And this is giving an answer of 272.73 ohms. This is the total resistance for loop 1, the parallel combination total resistance. And therefore we can calculate what is the voltage drop across this loop. Voltage is the product of current and the total resistance. And it's already given, the current is 23 milliamps. So here the current flowing, which is 23 milliamps. That means it is 23 times milli. The prefix milli has a value of 10 to the power of negative 3. So 23 milliamps is 23 times 10 to the power of negative 3 amps. So let us use that numbers here. So the current is 23 times 10 to the power of negative 3 times. The total resistance is 272.73. And this one on calculation, it is giving an answer of 60. Please make use of your calculator to get the correct values. 10 to the power of negative 3. And when you're writing it in the standard form, it is giving an answer of 6.27 volts, which is approximately 6 volt. This is what the question says. Show that the voltage is about 6 volt. So we are getting it as 6.7 to about 6 volt. Now the second part of the question is calculate the power dissipated by the thermistor. So power dissipated by the thermistor part. So let us see the circuit again. The power dissipated by thermistor. So for that we have to see, we have the different equations for the power dissipations. So as we know, the power dissipated is the product of voltage and current. So let us make use of this equation here. For that, first of all, we have to know how much is the voltage. The voltage across the thermistor, V of thermistor. This is the voltage of the thermistor. And since the loop is in series with the thermistor, the supply voltage 12 volt is distributed between the loop and the thermistor. And the loop voltage, we already see that it is 6 volt. So here we see that the loop voltage is 6.27 volt. Therefore, to calculate the thermistor voltage, it is 12 minus 6.27. So let us calculate that voltage. The voltage of the thermistor. The voltage of the thermistor, it is the supply voltage, V of the battery or cell. It is a battery here. V of the battery minus the voltage of the loop. Voltage of loop 1, which is 12 minus 6.27. This gives an answer of 5.73 volts. This is the voltage across the thermistor. Therefore, the power dissipated by the thermistor, power dissipated by thermistor equals, so this is the equation I'm going to use. It is the voltage of the thermistor times the current flowing. It is connected in series, so the same current is flowing through the thermistor and through the parallel combination loop. So thermistor voltage is 5.73 times there is a current of 23.10 to the power of negative 3. This is giving an answer of 131.79 times 10 to the power of negative 3 watts, which is dividing by 1000. So it is 0.131 watts. So minus 3 means dividing by 1000. So I'm moving the decimal place to the left, 3 places to the left, so which gives an answer of 0.131 watts. So this is the power dissipated by the thermistor. Now let us see the next part of the question. The student decreases the temperature of the thermistor. Explain the effect of decreasing the temperature on the ammeter reading and on the voltmeter reading. So if you are decreasing the temperature of the thermistor, let us see what is the voltmeter reading and the ammeter reading. So let's start writing the answer. As the temperature decreases, and we know that the thermistor resistance is depending on the temperature. So it is inversely proportional to the temperature. So this is the relation between them. So as the temperature decreases, the resistance of the thermistor increases. According to this relation, the resistance is increasing. When the resistance of the thermistor increases, the total resistance of the circuit is increasing. Total resistance for the circuit, it is increasing, which means the current of the circuit is decreasing because the voltage is as battery voltage constant. According to Ohm's law, when the resistance increases, the current is decreasing. Ohm's law means V is equal to I times R, IR. Okay, so the circuit current decreases means the ammeter reading is decreasing. So let us write the conclusion. So ammeter. Well, please make sure when you are writing the correct words. The ammeter reading decreases. Okay, Now, let's see what's happening to the voltmeter reading. So, the ammeter reading decreases means the current is decreasing. Therefore, the voltmeter is connected, or see, the voltmeter is connected to measure the voltage of the loop. So, the voltage of the loop is the total resistance of the loop times the circuit current. So, we can write the voltage of the loop, which is the circuit current times the total resistance of the loop. So the total resistance of the loop is not changing because these are two fixed resistors. 50, 500 and 600, 250 resistors, two fixed resistors. So R total remains the same, but the circuit current is decreasing. Therefore, the voltage of the loop also decreases. So let us write as I circuit decreases, voltage of loop decreases since R total is constant. It is not changing. R total is not changing. R total of the loop is not changing. R total of the loop, which is a parallel combination of two fixed resistors. R total of the loop is constant. So according to Ohm's law, when current decreases, the voltage of the loop is decreasing. See, voltage of the loop means that is the voltmeter reading. So voltage of the loop decreases. So we can write a conclusion. So the voltmeter reading also decreases. This is the question. They are asking how the voltmeter reading changes and how the ammeter reading changes. So the ammeter reading decreases. Along with that, the voltmeter reading is also decreasing. Now let's move on to the next part of the question or next question, question number 34. It's 23 June. Part of an electrical circuit is shown here. In 60 seconds, these many electrons are passing through point Z. Show that the current at Z is about 1.3 A. So we have studied that the current at a point is the rate of charges flowing through that point. So we have studied current is the rate of flow of, so it is dq by dt. This is what we say that current is the rate of flow of. Current is the rate of flow of charges. Okay. So, or in another way we write current is Q over T. And here in 60 seconds, so time is given, 60 seconds. This is the time, but Q is not given. But Q is, see, quantization of charge. Quantization of charge. See, the total charge in a coulomb, 1 coulomb is equal to number of electrons times or the total charge, 1 coulomb or total charge, total Q in coulomb. It is the number of charges times Q of an electron. This is the equation I'm going to use. So what is the total charge? When 4.8 times 10 to the power of 20 electrons are passing. So Q is N times charge of an electron over T. So this is how many electrons? It is 4.8 times 10 to the power of 20 electrons, and the charge of an electron, which is 1.6 times 10 to the power of minus 19 coulomb. This is the charge of an electron. So total charge Q in coulombs, it is the number of charges times the charge of an electron. So I'm writing that one. QE, N times QE. Q is 1.6 times 10 to the power of minus 19. This one. Charge of an electron. This is what I have substituted here over a time of 60 seconds. And on calculation, we are getting this as the total current passing, we are getting as 1.28 amps, approximately 1.3 amperes. This is what they are asking. Show that, again, show that the current is 1.3 amps. So we are getting it. So the total charge is the number of electrons. This is the one. Total charge is number of electrons times the charge of an electron. Okay. So let's move on to the next part of the question. In 60 seconds, the resistor transfers 24 joules of energy. Calculate the potential difference across the resistor. It is the energy is given, E, and the time is given. It is 60 seconds. Therefore, we have to, time is given 60 seconds and energy is given. So calculate the potential difference. We know that potential PD, potential difference is nothing but it is the voltage. And we have an equation relating the voltage, or we have studied as a definition, voltage is the energy transferred by unit charge. So here the energy transferred is, so I can write V equals E over Q, and the energy transferred is 24 joules, and the total number of charges we have not calculated here separately. Let me calculate one more time. Q is the number of charges times the charge of electron. So which is the number of charges? We have already seen 4.8 10 to the power of 20 times the charge of an electron 1.6 10 to the power of minus 19. So this is the total charge. Total charge, this one. Total charge is charge of an electron. This is charge of electron. The data booklet, they will give you the charge of electron. So you multiply with the number of charges. Therefore, the PD developed is 0.31 volts. Energy over charge. Energy over charge. Total charge is total number of charges times the charge of an electron. So on calculation, it is giving the PD as 0.31 volt. Now let us move on to the next question. A student investigates the terminal resistance of a cell using a circuit shown. The student used the variable resistor to vary the reading of the ammeter. He recorded corresponding readings from the voltmeter, and there is a graph given. So there is a variable resistor. This is the variable resistor. Then the cell. Okay, so the reading is given here. Determine the EMF of the cell and the internal resistance of the cell. And we know that EMF means EMF is the voltage given by, or the total voltage we get from the source when no current is taken from the cell, or no current is taken from the source. So EMF, the voltage of the source when no current is taken from the source. So from the graph, you can see that this is the voltage. On the y-axis, the voltmeter reading V, which is given here. So the voltmeter reading when no current is taken, and the ammeter reading or the current is given along the y-axis. So this is the ammeter. Ammeter reading, so current. So according to the definition, the EMF is the voltmeter reading when no current is taken. So no current is taken means when current is zero. So this is the point when current is zero. When current is zero, what is the voltage? That is the EMF. So to find out that, you use the ruler and draw a line backward to extend the line. So we can let me extend it, that is the y-intercept. Let me extend it backward, but when you are doing, please do it with a ruler and make it as a straight line, join with the line. So this is the y-intercept I'm getting. This is the y-intercept. Okay. So here, according to the definition, EMF means the voltage of the source when no current is taken from the source. And as from the graph, so EMF equals the y-intercept. And here, when I'm extending the line backward, I'm getting the y-intercept as it's between 1.6 and 1.4. So it is approximately 1.5 volts. So this is the EMF, which is 1.5 volts, the y-intercept. So the EMF is 1.5 volts. Now the next part of the question is calculate the internal resistance. The internal resistance. So let's see. So EMF we found the EMF already. Then the next one, the internal resistance, P part, the internal resistance R. Internal resistance equals the gradient, the negative of the gradient. Because from the graph we are getting the gradient is negative R. Therefore, to get the R value, the negative of gradient. So R is equal to the negative of the gradient. So let us calculate what is the gradient. The gradient here, you select 2 points in such a way that you can read its x coordinates and y coordinate properly. So I'm going to select the point, I'm going to select this point. This point I'm going to select, which is giving a corresponding current of 0.6 and what is the corresponding current? I can select this point and 0.6. Oh yeah, I can select, I think I can select these 2 points because I can read this also. So this point, these are the 2 points I'm going to select. So I'm going to make a triangle joining these two, the gradient. Okay. So on calculation, so I have 0.6 here and 1.2 here. So I'm writing here gradient. Delta y over delta x, and the y values are, this is giving a value of 0.6 and this one gives a value of, maybe it is 1.1. So Final value is 0.6, 0.6 minus 1.1 over the x value is 1.2 minus 0.6. So on calculation, this is giving an answer of 0.5 over 0. Yeah, 0.6. 0.5 over 0.6, and with the negative number, this is a negative 1. You can select the other points also. You can select even this point also. You can select this point and the last point. So this is giving an answer of 0.5. 0.5. It's giving an answer of 0.83. 0.83. Negative 0.83. Okay, you can try with other points also. Like, so I have taken these 2 points, this first point and this as a second point. If you want, you can select a third point between point 0.3 and point 0.2, or point 0.3 and 3 and 1. You can select it and use it. So I'm getting an answer of negative 8.83. So here negative of the gradient means, or the gradient is 0.83. So I'm getting an answer of 0.83 ohms. So these are my answers. 0.83 ohms, and I'm getting the EMF of 1.5 volt. This is the EMF and gradient I'm getting. Okay, now let's move on to the next part of the question. The student placed an identical cell in series with the original cell in the circuit. He connected the voltmeter across both the cells and repeated the investigation. The student plotted a new graph of these voltmeter and ammeter readings. Describe how the new graph is different from the graph for one cell. So this was the graph for one cell because he used only one cell here. But the next trial, or the next step, what he did is he used two identical resistors in series. So instead of a two identical cells. So he connected two identical cells like this. So this is EMF 1 and this is EMF 2. So when two identical cells are connected, or two EMFs are connected in series, the total EMF is the sum of individual ones. Therefore, here these are two identical ones, and we already calculated one as 1.5 plus 1 point. From the graph we calculated. So now the total EMF is 3 volt. And how is the internal resistance changes? Internal resistance, when you are connecting to two identical resistors in series, the internal resistors, say this is R1 and this is R2, then they are just getting added up, R1 plus R2. So we already got it as 0. How much you got? 0.83 plus 0.83. So double the value, which is 1.66 ohms. So this is the new internal resistance, and 3 volt is the new EMF. So the question is, describe how the new graph is different. So here you are getting the y-intercept as 3 volt. EMF is the y-intercept. So y-intercept as 3 volt and the gradient is more. That means you will get a new graph has a steeper gradient. You see that new gradient is increased. So the new gradient or new graph has a steeper gradient and with the y-intercept double the first value. So we can write as a conclusion. So the new graph has a steeper gradient, higher gradient, and the y-intercept has been doubled. Okay, so the new graph, the y-intercept which be 3 volt and it is a steeper gradient and y-intercept is 3 volt. This is the change that is happening in the graph. The new graph has a steeper gradient and the y-intercept has been doubled. Even steeper gradient means even the gradient also has been doubled. You have seen that the gradient also doubled. So I didn't mention that here, but you can say that here the gradient is doubled. This is what they have asked. Describe. No need to draw. Describe how the new graph changes. Let's move on to the next part of the question. The circuit shown contains a fixed resistor and a light-dependent resistor LDR. Explain why the power dissipated by the whole circuit changes as the intensity of the light incident on the LDR decreases. You should include the changes in the resistance of the LDR as the light intensity increases. This is a star question. Okay. So you have to develop the ideas correctly. You have to develop the ideas. So let's start with they are telling when the light intensity increases. So let's start with the light intensity. So as light intensity falling on LDR increases, what's happening? We know that the resistance of the LDR is inversely proportional to the light falling, light intensity. This is a relation between resistance and light. So when the light intensity increases, what happens? The resistance of the LDR. So the resistance of the LDR decreases by this relation. But here what they want is, this is what the first look, this is what we understood. But they are telling you to write the answer why the resistance of the LDR changes as the light intensity increases. Okay. So this is what we know as LDR intensity, light intensity falling on the LDR increases, the resistance is decreasing. So let me write it here. As the light intensity of the falling on the LDR increases, what's happening? The electron, so I'm starting from here, okay? It's as a conclusion I gave in the beginning itself, but let us start from here. As light intensity falling on the LDR increases, the electrons gain energy, light energy, and more electrons from valence band to conduction band. Because the LDR is made up of semiconductor material. LDR is made of semiconductor material. Okay, so here we see that as light intensity increases, electrons gain more energy and more electrons move from valence band to conduction band and become free. So in short, we can say that as temperature increases, number of free electrons increases. So as the number of free electrons increases, the current conduction increases. So there are more free electrons available to conduct the current. So current through the circuit increases, or current through the LDR, the current flow through the LDR. No need to say current through the circuit, the current through the LDR increases because more electrons are available now. So current through the LDR increases or current of the circuit increases. So as the current of the circuit increases, we can say that resistance of the LDR is decreasing. So this means, next one, so the resistance of the LDR decreases. This is the first part. Actually, they want about the power dissipation, but you have to write why the resistance of the LDR changes as the light intensity increases. So let us read from the beginning. As the light intensity of the LDR increases, electrons gain more energy. So more electrons move from valence band to conduction band and they become free. So number of free electrons increases. So the current through the circuit or current through the LDR increases. Accordingly, the resistance decreases. So I'm writing it here also. As temperature increases, number of free electrons increases. So current increases and resistance of the LDR decreases. In short, this is the way you can write the answer. Now let's move on to the next part of the question. The next part, what they are asking is explain why the power dissipated by the power dissipation. Okay. So here we see that the resistance of the LDR decreases. That means the current through the LDR increases. Therefore, we can say that power dissipated. Power dissipated by the circuit, which is equal to current of the circuit over the voltage. And here the voltage is the supply voltage, that is the cell voltage. The cell voltage is fixed, it's not changing. And through the fixed resistor as well as the LDR, the same current is flowing. This is I of the circuit. The same current is flowing through the LDR as the LDR current. LDR current is equal to I of the circuit. So using that idea, we can say the power dissipated by the circuit, I'm just writing P equals I of the circuit times the voltage. Voltage here, it is the cell voltage. Okay. Then I can write, since V of the cell is constant, it is not changing, power increases as I circuit increases. So this is what they want. You have to show that the power dissipated by, explain why the power dissipated by the whole circuit changes. So the power dissipated by the whole circuit changes because the current through the whole circuit or the circuit current is increasing. Accordingly, the power dissipated is also increasing. So power increases as the circuit current increases. Now here we are using it. V of the cell is constant. Therefore, power and I circuit are uh, increasing the same way. When a circuit current increases, the power is also increasing. Now let's move on to the next question. Question number 37. The drivers use car headlights to emit light in dark conditions. The graph shows the current and voltage variation of a car headlight. VI graph or IV graph of a car headlight it is given. So IV graph of a car headlight, the current and the voltage. Now determine the minimum potential difference for which the headlight will emit light and when the power dissipated is 35 watts. The headlight will emit light when it dissipates at least 35 watts power. Determine the minimum potential difference. So we have to get the power. We have an equation, power dissipated is the product of current and voltage. And here the power dissipation must be 35 watts. So for that, what should be the minimum potential, minimum voltage? So let us see one by one. At 6, the current is 3.2. So 3.2 into 3.2 times 6 is the number it is giving. 6 into 3.2 is giving a value of 19.2, very less. 19.2, it's very less, very small this one. So let us increase the voltage. 7, 8. At 8, it's a trial and error method way I'm doing. At 8, the corresponding current here, at 8, the corresponding current, it is around 3.5, it is around 3.8. So 3.8 into 3.8 into 8 is 3.8. It's giving a value of 30.4. We are nearing. It is giving a value of 30.4 watts. But we have to get 35. So let us try with the 9. Yeah, I think with the 9 you will get. With the 9, there is a current of, what is the current coming here for this point? This point, current is around 3.9. 3.9 amps. So it is 3.9 amps. So I think you will get it here. The voltage 9 times 3.9. It's giving a value of 35.1. Oh yeah, it's okay, 35. So we are getting a value of 35.1 watts. So this is what we are getting. Okay, so 35 watts. So we are getting the answer. Yes. So this number is 35.1. So the minimum potential difference must be 9 volt. So PD minimum equals 9 volt. Now let's move on to the next part of the question. The car, two headlights are connected in parallel. In fact, or actually, two headlights are connected in parallel with the 12-volt battery. Explain the advantages of connecting headlights in parallel. Yeah, this we have studied what are the advantages of connecting bulbs or the components in parallel. It's a 3-mark question, so let's try to write at least 3 points. So, first one is parallel connection advantages. If one headlight fails, breaks, the other one still remains on. That is the first advantage. So, number one, if one headlight fails, the other one remains on. The one remains on. That means it will still working. Now the second advantage is you studied that in parallel combination each component is getting the same voltage. So each headlight will receive same voltage. That is same battery voltage 12 volt. So what is advantage of this? Both will have same brightness. Same brightness or both will have same power. So same brightness. Now as a third advantage we can say compared to series it is the same only. Both will have the same voltage. Therefore, but if it is in series, it's not the third one. If in series, if the headlights are in series, each one will get, each light will get only 6 volt because the 12 volt will be shared between the two headlights. So each one will get only 6 volt. Therefore, brightness will be less if they are connected in series. But since we are connecting them in parallel, both will have the same brightness or more brightness. Okay. So as number 3, we can write the lights will have more brightness. Brightness than connecting them in series. So same brightness, more brightness, and even if one fails, one headlight fails, the other one remains on. Now let us move on to the next question, next part of the question. A student writes the following statement. When connected to the 12-volt battery, the combined resistance of the two headlights in parallel is 1/4 of the combined resistance of the two headlights in series. Deduce whether the student is right or wrong. Your answer should include calculating using data from the graph. So from the graph, connected to the 12-volt battery, parallel or a series. So the total resistance here you have to connect from the battery. So let us see when they are connected in series or parallel. So first of all, let us see what is the resistance. What is the resistance of one lamp? so that we know the current and voltage. So you take any particular voltage and calculate the resistance. So as an example, when you are taking the current voltage, you can take the gradient. Actually, it is the gradient is the resistance. So if we take a particular value, this is the value we can take. Let us take maximum 12 and 4.5. 12 by 0.5. So I'm taking a voltage of 12, the maximum voltage of 12 with a maximum current of 4.5, approximately 4.5, 4.6 it is. It's 4.6. For a voltage of 12, the current is 4.6. It's not. Okay. So let's calculate from the graph. So I'm starting from the graph. From graph, resistance equals the voltage. Battery voltage is 12 and the corresponding current is around 4.6. So how much is the value we are getting? 12 over 4.6 is giving you a current of a resistor of 2.6 ohms. See, I have used the maximum voltage 12, that is the Vmax, the battery voltage, and the current. The current is little above 4.5, little above 4.5. So this is the Imax, the maximum current, maximum circuit current and the maximum voltage I used. So I calculated the resistance from here. Resistance R equals Vmax by Imax. This is the way I calculated and I got it as 2.6 ohms, around 2.6 ohms. That is what I have done it here. From graph, R is 2.6 ohms. Now let's see the series connection. Yeah, so let us take series. If they are connected in series, R total is 2.6 plus 2.6. Total resistance will be the sum of these two, which is 5.2 ohms. 5.2 ohms. Now let's see when they are connected parallel. It is 1 over R total is 1 over R1 plus 1 over R2. But I hope you remember we are going to use the shortcut like it is the product over the sum. Product over the sum. So this will give 2.6 times 2.6 over the sum is 5.2 and this will give an answer of 1.3 ohms. So when they are connected parallel, RT parallel is 1.3 and RT series is 5.2. What is the question demands? The question says that the student said the combined resistance when it is in parallel is 1/4 of the combined resistance in series. Deduce whether the student is correct or not. So let us check that. So from here, I don't have place here, so I'm just using it. I'm using the space here. Let's see, it is easy to calculate what is the 1/4 of RT series. So we have RT in series, which is 5.2. Let's calculate 1/4 of RT series. 1/4 of RT series is 1/4 of 5.2. How much is 1/4 of 5.2? It is 5.2 over 0.2. over 4, which is giving an answer of 1.3. Yes. So this is giving an answer of 1.3 ohms, which is same as RT parallel. So from this we can say that the student is correct, because the student said RT parallel is 1/4 of RT series. It is correct. So we are getting, so student is correct. Is here. So student is correct. RT series is 5.2, RT parallel is 1.3, which is 1/4 of. Okay, so I'm writing here RT series equals, in another way I can say it is 4 times RT parallel. So student is correct. Another way I wrote it, parallel is 1/4 or series is 4 times. So the student is correct. Now let's see the next part of the question. The headlights are connected in the circuit using copper wire. Calculate the drift velocity of the electrons in the copper wire, the number of charge carriers, resistivity, resistance per unit length of the wire. It's given. Calculate the drift velocity of the electrons. So we have the relation relating all of them. I is equal to N, Q, V and A. So V means Vd, drift velocity. So drift velocity Vd is I over N, Q and A. Now let us check one by one whether the all data are provided. The current in the wire. So current is given. I is given. Then the number of electrons, number of carriers per. So it is number density is given. N is given. Then the resistance per unit length. That is the resistivity. Resistivity is given. Resistivity of copper 1.72, and this is resistance per unit length of the copper wire is also given. So using the resistance per unit length of the copper wire is ohm per meter. Okay, so this is nothing but the resistance is given. So we have to calculate the area first. So let us calculate the area. Area is how much? This is what we have to calculate. So for that, let us use a relation R is equal to rho L over A. Therefore, area equals rho L over resistance. So this is what first you have to calculate. So on substituting all the values, we are getting the area as 9.83 times 10 to the power of -7 meter square. This is the area we are getting. So let's make use of that number here. Current is 4.6 over n is 8.49 times 10 to the power of 28 times the area is 9.83 times 10 to the power of negative 7, and all of them on calculation, it is giving the drift velocity as 3.4 times 10 to the power of negative 4 meter per second. This is the drift velocity given. Here I calculated the area. Area from this equation, R is rho L over A, and all the values are given. Length is given, rho is given, then resistance is given. So using all these values, we calculated 9.83 and I substituted here. So the drift velocity is 3.4 times 10 to the power of negative 4. Let's move on to the next question. A geophysicist may use resistivity to determine the different materials within the ground. The electrodes and 12-volt battery are connected to 2 points 0.8 meter apart in the ground. Calculate the resistivity of the ground between the electrodes. See, between the electrodes, the length is given. So this is the length. This is the length given. The voltage is there. Then the current between the electrodes, it is given, which is 8.5 times 10 to the power of negative 3 amps. Then the area is given. This is this much amps. Area is given. So calculate the resistivity. So let us make use of the equation R is equal to rho L over A. But here the resistance is not given separately. So we have to calculate the resistance first of all. Or here itself I can write, and we have the equation resistance is equal to V over I, Ohm's law. So I'm using those equations here. Instead of resistance, I'm writing V over I equals rho L over A. So using these two equations, I can write, calculate the resistivity. Rho equals, making the cross product, is I times L over V times A. So when I'm using all these numbers, I'm sorry, this is not the way equation. I flipped the equation by mistake. It is V times A. So we have rho equals VA times I L. What is the voltage? Voltage is 12. Then the area is 0.25 over the current is 8.5 times 10 to the power of negative 3 times the length is 0.8. So on calculation, this is giving a total resistivity of 441 ohm meter. 441 meter. This is the answer I'm getting. It's a simple question. The resistance is not given, but we can calculate the resistance using. So these are the two equations I'm using. So we can calculate them. Then the next part says that, or next part is given a graph. Explain how the sketch corresponds to the graph. Explain how the sketch corresponds to the graph. The sketch is this one. So ground level, the first level directly under the ground is the topsoil, then the wet soil, and at a depth of 5 meter, the bedrock, it's full of rock, the bedrock starts. And also you see that initially the resistivity is decreasing. Resistivity is decreasing till 5 meters. and then it increases suddenly and remains constant. It remains as a constant. Resistivity remains as a constant here. So these are the informations we are getting. So explain how the sketch corresponds to the graph. So from the graph, relating the graph and sketch, we have to explain. And we see very clearly one thing in the beginning, the resistivity keep decreases till 5-meter depth from the topsoil to the wet soil. So this is what we can write in the beginning. Resistivity decreases from topsoil to wet soil, and lowest and the lowest for wet soil, lowest for wet soil at 5-meter depth. Then after that, what is happening? At 5 meters, the resistivity increases suddenly. At 5 meters, resistivity increases suddenly and remains constant. Remains constant, and this indicates that, see here you see that the resistivity remains constant here. That means it indicates that below 5 meters, there is a constant depth of bedrock. Okay. So at 5-meter, resistivity increases suddenly and remains constant, indicating, what is the indication we are getting? Indicating the, as a third point it will come here, indicating and indicating the constant, indicating the constant depth of bedrock. So this is the explanation we can write relating the sketch and the graph. So resistivity is decreasing from topsoil to wet soil. Resistivity decreases from topsoil to wet soil, and the lowest at 5-meter. Then at 5-meter increases suddenly and remains constant, indicating a constant depth of bedrock. Bedrock below 5-meter depth. Now the next part of the question, they are telling that apart from the first 2 electrodes, 2 more electrodes are connected at a distance of 2 meters with a new voltmeter. Explain the value you would expect to observe on the voltmeter if the cross-sectional area of the ground through which the current passing were constant. So everything remains constant. That means they are telling the area constant, I constant. All these things remains constant. Only the length has changed. Okay. Actually, we know that the resistance, we write it here. We know that the resistance is proportional to the length. Resistance is proportional to the length. The voltmeter reading we have to see. And also we can say that the voltage is proportional to the resistance, because V is equal to when I constant, see I'm using this way. When I constant, voltage and R are directly proportional. V is equal to I times R. And also we know that as the length increases, the resistance is increasing. So using these two relations, we can say that, see, there is a direct relation between length and voltage, because R is common. See, here R is there, here also R is there, R is common. Therefore, we can write, that means V and length are proportional. So here, for the first V value, first R value, the voltage is first length. This is the length. First length between two electrodes, the voltage is 12. Therefore, for 0.2 meter length, what is the new voltage? This is what we are going to calculate. So we can write it as new voltage over V is equal to new length over the original length. So that means, what is the new voltage we want to calculate? V of new, original one is 12, and new length is 0.2, and the original one was 0.8. So on calculation, we get the new voltage as 12 times 0.2 over 0.8. This will give an answer of 3 volt. So this is the expected value. They said current and area remains constant. But we know that R and L are directly proportional. Since I is constant, V and R are proportional using these two. So let me write 1 and 2. So I'm writing from 1 and 2. From 1 and 2, I can say V and L are directly proportional. So using that direct proportionality, I'm calculating the value of new voltage as 3 volt. Now let's move on to the next part of the question. Give one reason why this method leads to more accurate result than the method described in part A. This method means they reduce the length. They reduce the length of placing the electrodes. Give a reason why this method leads to more accurate result. See, they were calculating. You look at the initial part, they were calculating the resistivity. Okay. So the resistivity is depending on the resistance. So let's see, is there any change in the resistance, or how it is related with the resistivity. Now here, one thing is very clear, that we are using only less length used here. So when there is less length used, the resistance or resistivity will be less. So we can say less resistance or less resistivity over shorter length. And also cross-sectional area will be more constant. So we can write less resistance or resistivity over short length. So more accurate. Result of resistivity. Let's move on to the next question. There is a potential divider is given here. The question is, deduce whether the circuit would switch on the heater when the temperature falls below 10 degree. When the temperature falls below 10 degree, you should include calculation of the PD across the thermistor when the temperature is 10 degree. So where is the temperature 10 degree? Here we have temperature 10 degree here. This is 10 degree temperature. PD across. So for that 10 degree temperature, we are getting the corresponding resistance. Resistance as 2 ohms. So let's write that one. It's a 6-mark question. So whatever we observed, let us write that. At 10 degrees centigrade, from the graph, at 10 degrees centigrade, the resistance is 2 ohms. From the graph, at 10 degrees centigrade, resistance is 2 ohms. This is the observation we got. So resistance of the thermistor, we got it as 2. So here we got the resistance of the thermistor, R of the thermistor is equal to 2 ohms. This is at 10 degrees centigrade. Therefore, we can calculate what is the voltage drop across this resistor. Okay, you can calculate here or here you can calculate and say voltage drop across the thermistor. So let's calculate the voltage drop of the thermistor. So voltage drop across the thermistor is the I circuit times the resistance of the thermistor. This is the thermistor resistance of the thermistor. Now I circuit is the total voltage over the total resistance, that is 15 plus 2. The total I circuit is voltage over 15 plus 2 total resistance times resistance of the thermistor, which is 2 again. So let us calculate 12 times 2 over 17. And this will give an answer of 0.7. So this is the thermistor voltage. So if the thermistor, if the temperature goes below 10 degree, the resistance increases and the PD of the heater is increasing. So what they are asking you here is you should deduce whether the circuit would switch on the heater when the temperature falls below 10 degree. So here you can see that if the temperature goes below, the resistance is increasing and the PD of the heater is, or the PD across the thermistor is increasing. So the heater switch does perform the required action. So you can write if temperature goes below R increases, and PD of the PD increases. So the heater switch can perform as required. Okay, let us move on to the next part. Explain why the resistance of the thermistor changes with the temperature. Explain why the resistance of the thermistor changes with the temperature. As temperature changes, can be increase or decrease. So as the temperature changes, the electrons by thermionic emission changes. As temperature changes, because thermistors are made of semiconductor material. So I'm writing that one as temperature changes, R changes. This is as a conclusion I wrote it. So let me write thermistors are made of semiconductor materials. As temperature changes, electrons emitted by thermionic emission changes. So current changes and resistance of the thermistor changes, because resistance of the thermistor is proportional to the temperature. Now let us move on to the next question. Two resistors are connected in a circuit as shown. The question is, derive the equation in this form. The total resistance in parallel combination you have to get this as the equation for the total resistance when the resistors are connected in parallel. So here you see that the current starting from the battery, when it reaches here, according to conservation of charges, so anyway, it branches out into two currents. Say it is I1 and I2. So the total current I must be equal to I1 plus I2 according to conservation of charges. Okay, so let's start with that. According to conservation of charges, I equals I1 plus I2. Okay, it branches into two parts. So I means this is a circuit current. Circuit current is the total voltage V over the total resistance of both of them, which is equal to the individual currents are, say, individual voltage V1 over R1 plus the individual voltage V2 over R2. Okay, so let us assume this voltage drop is V1 and this voltage drop is V2. But we know that in parallel combination, total battery voltage is equal to the individual component voltage. That is, we can cancel all of them. That is 1 over RT equals 1 over R1 plus 1 over R2. Because we can cancel V1, V2, V3 because they are equal. So this is what we are getting. And from this, we can take the value of 1 over R1 plus 1 over R2, that is 1 over R total equals R1, R2, the LCM, R2 plus R1. Therefore, RT, when you are flipping it, RT is R1, R2 over R1 plus R2. This is the way you can prove it. So we reach till here, then we are taking the LCM R1 time R2, then flipping and getting the value of R total alone. So it is R1 R2 by R1 plus R2. Let's move on to the next question, 23 November. Calculate the thickness of the layer of carbon. So they are telling about resistivity paper is paper covered with a thin layer of carbon paper. Its length, width, it is given. Then the resistance between the ends of the resistivity paper is 8.8 ohms. That means the resistance is also given. The resistance is given, resistivity is given, length and width, etc. are given. So the question is calculate the thickness of the layer. So thickness of the layer means this somewhat like this height. This height you have to calculate, thickness. This is the thickness, height. Height or thickness you have to, it's not like this way. The thickness, height this way. This thickness you have to calculate. Okay. Here we know that the relation between resistance, resistivity, etc. resistance is rho L over A. This is the relation we are using. So it says that there is a resistance of 8.8. So 8.8 equals, what is the length? It is 12 centimeter. So this is the length. This comes as the length. Centimeter, I'm changing into meter. Length over, now area. Area is the width. What is the area? Height times the width. This height times the width will come as the area. So area, here I'm writing area equals 4.2 times 10 to the power of minus 3 times the height, the width or the height. Or let me write it as width itself, width. This height is coming as the width. This height is coming as the width. So here I can say it is 4.2 times 10 to the power of negative 3 times width. So using this information, we can calculate what is the width. Width equals, on calculation, we are getting Actually, there is no need of doing this way. We can calculate the width is, I'm not doing the calculation. I'm just using the calculation altogether. 12 into 10 to the power of negative 3 over 4.2 times 10 to the power of negative 3 times 8.8. This is the width we are getting. Width, or this is the height we are getting. So on calculation, it is giving me an answer of 1.2 times 10 to the power of negative 5 meters. This is the width I'm getting. So they're asking you to find out the width or the height. For that, I'm using this equation, rho L over A. This L is the length 12 centimeter and area will be the width times 4.2. This is the area. So this area only coming here. I'm substituting everything and I'm getting an answer of 1.2 10 to the power of negative 5 meters. Now we are coming to the next part of the question. A student connected the ends of the resistivity paper to a cell of EMF 1.5 and a voltmeter as shown. The reading on the voltmeter was 1.4. Calculate the terminal, calculate the internal resistance of the cell. This is a direct question. Many times we have done these type of questions. We have the complete equation. It is EMF is V plus I times R. So it says that there is an EMF of 1.5. This is E. So 1.5 equals, record on the voltmeter, that is V 1.4 plus IR. So we have I times R equals 1.5 minus 1.4, which is 0.1. Therefore, R equals 0.1 over I. The current is also given. Current we can calculate, actually it is not given, so we are going to calculate the current here separately. See, it says that the terminal PD is 1.4 volt. V equals I times R. So this is I times the resistance is getting us 8.8 because it's already given here in this question. They said the resistance of this resistor paper is 8.8 ohms. It's given. What that information we can use here. So it is 8.8. Therefore, I equals 1.4 over 8.8, which is giving an answer of 0.15 amps. So this number 0.15 amps, I'm going to use it here, current. So this is 0.1 over 0.15, and on calculation you are getting resistance 0.66 ohms. This is the internal resistance. Now coming to the last part of the question. Connecting to the right hand terminal of the voltmeter was moved to a distance of 3 centimeter from the left hand side of the resistivity paper. Determine the reading on the voltmeter. So actually what they are telling here is the resistivity paper. You have seen the resistivity paper. This was the resistivity paper. Sorry. The resistivity paper little magnified way I have drawn. That's all. Okay. So the length was 12 centimeter. This was the length. Now they are telling the length is reduced to a new value of 3 meters. The length is now only 3 meters. That is this part, only 3 meters. 3-meter length from the left side. Okay. And we know that resistance is proportional to the length. And also reading on the voltmeter. So voltmeter reading is proportional to the resistance. Because I constant, Ohm's law. When I constant, V and R are directly proportional. So using these two, see we have seen that R is directly related to L. R is also related to V. That means we can say that V and L are related. That means the voltage nu over V is same as length nu over the original length. The new length, the new voltage we want to calculate. So V nu over the original length was, original voltage was, what was the EMF given? It was 1.5. It's not 1.2. No, the original voltage was, voltmeter reading was 1.4. It is not 12. Terminal PD was, it is 1.4 equals, so we got the new length as 3 meter over the original length 3 centimeter. 3 into 10 to the power of minus 2. And the original length was 12 into 10 to the power of minus 2. So from this, we can calculate what is the new voltage. It is 1.4 into 3 into 10 to the power of minus 2 over 12 into 10 to the power of minus 2. So on calculation, that is giving an answer of 0.35. This is the answer we are getting on calculation. Almost these type of a question, we have solved it before. We solved one question like the potential divider. In the potential divider case also, we have seen almost this type of a relation. Resistance and length are related. Voltage and resistance is related. Therefore, there is a direct relation between voltage and length. Same way it is solved here. This question, last question. So we are getting the new voltage as the voltmeter reading is 0.35. So I'm writing that as a conclusion, that is voltmeter reading 0.35